Hello, everyone. I'm Matt O'Dowd. Welcome to our 2022 end of year AMA live stream. This is becoming a little bit of a tradition now, so I kind of like to think of it as our state of space-time address, which means before we get into me trying to answer as many of your questions as I possibly can, a little overview of the state of the space-time. I mean the show as well as the uh, 3+1 dimensional entity, and look into what we expect for the next year of space-time. So I have, by the way, a lot of questions gathered from our community tab, but I'll also be trying to monitor the feed as I can to see if I can get some of the questions there, and I do apologize if I don't get them all. I guarantee I won't. So the state of space-time, well, I was looking through our video list and it's hard to even summarize because we covered so much in the last year, from fuzzballs to what happens if a black hole hits the Earth, other fun stuff like that. We got very fundamental. We talked about whether the universe is fundamentally informational, explored some of the interpretations of quantum mechanics, from objective collapse theory to, some more, let's say, shut up and calculate-ish approaches to quantum mechanics, like lattice, quantum chromodynamics, density functional theory, how you actually do quantum mechanics. We got pretty practical all the way down to diving deep into solid state physics, looking at quasi-particles, looking at potentially new elements on the periodic table. But we always swung back to about as abstract and fundamental as you can imagine, from superdeterminism to the idea that the universe is informational and created itself. So it was a wild ride, and thank you for staying with us on that journey. We try to keep setting the bar for ourselves, and we hope that 2023 will oscillate as wildly and more. But at this point, we've been making space-time for 7 years, and we've covered an awful lot. And what that means is that we're now able to somewhat synthesize our knowledge. And so we'll try to keep asking some very big questions, and our questions are going to become more and more meta. We're going to start asking questions about what it means to be doing physics. What is the project of science really? What is even beyond quantum mechanics, what is the role of the observer in doing physics? And on that note, there's an awful lot we can say in physics about what it is to be us, including topics on the physics of the mind, which is some hairy stuff that we will be delving into. And we'll keep coming back to the fun stuff, and hopefully at some point make a video announcing we discovered aliens. Don't count on it. So maybe I will start by launching into some of the questions from our community page. And rather than warm you up lightly, I'm going to leap straight in to a question from Bryce regarding block time. To paraphrase, the block time universe is often compared to a music record where the past and the future exist equally. But in that analogy, what is the needle that's playing the record? So, amazing question, Bryce. Always try to poke these analogies until they break. So to bring everyone up to speed, Einstein's relativity implies that the past and future exist because there's no absolute notion of simultaneity. Okay? There's no absolutely agreed current instant. So for any time in my own future, I can think about a reference frame somewhere else in the universe to whom an observer in that reference frame my future is their present or even their past. Ergo, the future already exists, and so does the past, and the universe is a 4D block of space-time with this sort of eternal existence to some abstract external observer. So that's the block-time universe. And so then the question is, why do observers inside the block experience this as a sequence of time slices, one after the other, played like some kind of flip book? Or in the analogy, like music extracted by running a needle along a record groove that itself has a fundamental existence from start to end. And what is the needle in this analogy of the block universe? So to answer this, we need to pick apart what an observer is. So an observer, first of all, is not external to the block universe, is inside the block universe. The observer encompasses a limited range of both space and time, like the needle point. So it's spatially localized, and it witnesses either a narrow slice or a thick slice of time, but something inside the block universe as its own experience of the current instant. So if we want our observer to experience anything at all and to be, for example, self-aware, okay, which is one of the criteria for the observer feeling a little bit like ourselves, then it needs to be able to somehow formulate a sense of self and ideally to have some internal model of the external world. So that self-awareness and the world model is going to take the form of some configuration of information within the observer's self, within the observer's reference frame. And you can imagine a static data structure that contained that information, like the decoding sense of self, like on a hard drive that didn't change over time. But such a structure would never be able to tell itself a story of its own self-awareness. And so it would be, in a sense, a frozen moment of awareness. So in order to, in the first place, develop this self-awareness and then to reflect and tell yourself a story of your self-awareness, the data structure needs to evolve. And it may not matter which direction in time or in which space that evolution happens, as long as it plays out in a particular way. So we can imagine the world line of our mind from birth to death existing as an evolving pattern of complexity that sort of just exists to an abstract external observer. But when we read that evolving pattern of complexity in the correct direction, it looks like that the pattern has an evolving awareness of its own state. Read it in the wrong direction and it's incoherent. Okay, so really there is no needle. There are just different frames of reference defined by the world lines of informational patterns inside the block. And some of those frames of reference are telling an internal story to themselves if read in the right direction. So who is reading the block in the right direction? Well, the embedded information pattern itself, its own self, in this sort of feedback cycle of self-observation, if you like. As for why this all happens in one time of direction rather than another, well, we did an episode on it. It's because of the asymmetry in the entropy of the universe that we perceive as a moment of very low entropy at the Big Bang. And for that, I will refer you to our episode, which I think is called The Arrow of Time and How to Observe It. Okay. Big answer to a small but profound question. Let me scan Grab and Laking. Yes, it is hypermeta, but the universe is a very meta place. Let's do something simple. Ganesh asks, why does light shine? Well, photons themselves don't shine per se. Photons just travel through the universe, have no conception of time. They start in a place and end in the place, and as far as they're concerned, that entire existence is but an instant. What shines is our perception of the endpoints of photons when they dump their energy on the retinas of our eyes. Okay, so photons don't shine, but we perceive shining because we have a mental construct of what photons landing on our retinas mean. Another one from the AMA, from the community tab. Let's get into black holes, actually. Black holes are, in part, my own research area. And I can answer them with some competence, unlike my waffling on the nature of the mind. So Wolverlad25 asks a couple of questions. First, when black holes evaporate, shouldn't they pop back into existence as a neutron star when the Schwarzschild radius shrinks below its critical size? And second, if we can never see anything fall below the event horizon, why would black holes be black? So it is true that a neutron star will only turn into a black hole when its mass is large enough so that the would-be event horizon becomes larger than the surface of the star. Then the event horizon actually becomes real and the star vanishes beneath it. If the star then loses mass and its event horizon shrinks, it's too late. Too late for the neutron star, because as soon as the event horizon forms, space-time within the horizon collapses to a singularity faster than the speed of light, carrying the star downwards, and so no evaporation can catch up to the collapsing star. And as for the color of a black hole, so it is true that from the perspective of a distant observer, everything that fell into a black hole is frozen forever on the event horizon, but it's still effectively black, because the light from the stuff on the event horizon is infinitely redshifted, so its wavelength has been stretched to the point that we could never detect it. And even material that's falling in quickly is redshifted to extremely low energy radio waves, rendering a black hole effectively black. The black hole of our theory is an ideal object that has already formed, but black holes in reality are nonetheless effectively black holes, as the Event Horizon Telescope has shown us directly. So here's a good one. So Tricky has extended a black hole question from their 6-year-old daughter, Celia. I apologize if I got the pronunciation wrong, but Celia asks, could the universe be an accretion disk? So, hi Celia, that's a very interesting idea. And so I want to remind everyone else who is not as smart in astrophysics. An accretion disk is a whirlpool of extremely hot matter that's falling into a black hole. So for the universe to be an accretion disk, we need to have, the universe isn't made of gas or plasma entirely, it's made of space and time. So we need to have the fabric of space whirling into a black hole. We don't have direct evidence for this. We have to check, for example, to see if the universe is rotating. And there is some evidence that there may be a very slight rotation to the universe, but that evidence isn't too compelling yet. I've been thinking of doing an episode on whether the universe is rotating, and to help answer your question, I should do that. However, I'm still not sure that it's rotating in the right way to look like it's falling into a black hole. On the other hand, other people have asked whether the universe itself might be a black hole, or the opposite of a black hole, which is a white hole, and we did an episode on that. Anyway, that is some very smart thinking, and even if this hypothesis doesn't work out, these are exactly the right sort of questions that we should be asking. Let me try to answer another question from our rapidly growing chat section. So Jason Wright asks a related question, might the universe exist as the event horizon of the Big Bang singularity? Yes, it might. Yes and no. So there's a couple of different concepts that get tangled up here. So one is the idea that the universe could be some type of singularity, some kind of black hole-like thing where the Big Bang is the singularity. And we did that episode. In this case, the universe would presumably be a white hole. And in that case, the event horizon of such a universe corresponds or could correspond to our cosmic horizon. And so the place where all of this might come together is in the concept of the holographic principle, also known in more technical terms as the ADS-CFT correspondence, in which for a particular type of universe, one which doesn't look exactly like our universe in the theory, but might still apply to our universe, there is a way to think about our universe as being kind of simultaneously existing as the volume of our universe with all of its gravity and all of its internal objects, stars and galaxies and so on, this 3D universe. And there's a simultaneous description on the surface of the universe, which we could think of as the cosmic event horizon. And on the surface of that universe, we can do an equivalent description in a slightly different theory called a conformal field theory. That's the CFT. And the two are what we call dual descriptions of each other. Okay, so the conformal field theory has a dynamics that gives us the internal universe, and it's been said that we can describe the internal universe, which we call the bulk, our 3D internal universe, as a hologram projected inwards from its boundary. So one thing I want to comment on here is that this is an example of something really key in physics. It's an example of what we call a duality, in which we have two physical explanations and mathematical theories that describe a phenomenon or the whole universe. And the two different theories seem to be in contradiction to each other, but describe exactly the same thing, lead to the same outcomes, produce all the same results, but they seem to give very conflicting stories, like that the universe actually exists on its own surface, or that it exists in the interior. It has been, I think, often very incorrectly described that the interior of our universe is actually an illusion and that we really exist on the boundary. And that is not what the holographic principle is saying. It's not what ADS-CFT is saying. What this is saying is that these two descriptions are equivalent. They are what's known as a duality, and one is not more fundamental than the other. And I wanted to bring that up because dualities in general are such a strange feature of our universe. We see them throughout a lot of our more speculative theories, like the holographic principle and string theory, but we also see it in regular physics. Dual descriptions of the same phenomenon, different stories that lead to the same observables, and understanding dualities, I think, is a key to the path forward, and it's something that we'll be talking about in the next year. All right, I'm going to quickly scan. All right, you guys ask excellent questions. DBZ GT, yes, black holes certainly are creepy. AppBurner1 asks, what happened to his teeth? Okay, well, that one I can answer. Okay, so I chipped it. It broke. I bit a particularly crusty loaf of bread and it broke, and the dentist is currently making the mold. But I promise you 2023 will be more toothsome than ever. It's a temporary gap, but I think it makes me look more like a Charles Dickens orphan, and I think it's very cute, but please don't worry about it. So the other thing that, one second, guys. Okay, so a few people in the chat have mentioned a topic that I should bring up because it is also part of the outlook, which is that we, so myself and some of my colleagues who are helping make the Spacetime program have another project, and the project is a film, and this will be a feature-length documentary. It's called Inventing Reality, and I talked about the past 7 years of space-time leading to this kind of synthesis, certainly in my own brain, of all these different subjects. And this film will, in a way, try to bring some of that together. It will be asking, firstly, the question, what is reality? But perhaps more importantly, exploring the meta questions of the knowability of the universe, of how our search for the fundamental is connected to what we are, as evolving patterns of information in the block universe. And can such a thing ever hope to understand the baseline clockwork of reality? And if that sounds like it might be interesting to you, then you could search for Inventing Reality on Indiegogo. And I promise you we'll tell you a lot more. And if and when we make the movie, we will make the movie. Let's see how well we can make it. We're going to go deep into areas that we could never do just in space-time with our 10-minute slots. Okay, we'll be able to do an awful lot more in a 90-minute feature film. All right, guys. Let me get to some more questions on. Here's a nice one. So let's go really deep. Mike Ubert asks if the universe itself, asks if perhaps the universe itself could be an example of retrocausality. Okay, and I take that to be asking, could the universe have caused itself? Okay, so retrocausality is often brought up in the context of the quantum eraser experiments, in which a choice to make one measurement or another can change the way particles behave in the past. And I think that the retrocausal interpretation of those experiments has been somewhat debunked, and we will do more episodes on why that's the case. But that said, so I would have also said that ideas about a retrocausal origin of the universe would also be bunk, pseudoscientific nonsense, except for two facts. So the first fact is that when you try to ask how did the universe first come into being, you end up with this sort of infinite causal regression. Okay, you're trying to push backwards to some first primal cause, and you have to start somewhere. So you either have a turtles all the way down situation, where things are causing things are causing things are causing things, and you never get to the first thing, or you have to question how fundamental the notion of causality even is, and perhaps allow some causeless initial state. The first turtle just was. Or you have to decouple cause perhaps from the effect of time, from being embedded in a unitary flow, a one-directional flow of time. And that would be a retrocausal origin to the universe. And the reason that last one maybe not, shouldn't be dismissed out of hand is just due to an appeal to authority, and that is that John Archibald Wheeler, okay, the guy who taught Feynman and many other great physicists, after many decades thinking about the problem of what was the primal cause, settled on something like this. He thought that the universe may have caused itself in what he referred to as a self-excited circuit. And in Wheeler's notion, the observer plays a part, although he's not sure that the observer needs to be a conscious observer, but somehow the universe either measuring or being aware of itself is what ends up leading to this creative cycle, this circuit. And we did an episode on it. It's called Does the Universe Create Itself? Okay, I don't have a stance on the subject, except that I'm not going to dismiss anything that John Archibald Wheeler spent decades thinking about. After the relatively few years that I thought about that, and me not being John Archibald Wheeler. Okay. So Daniel Lewis asks, what is my life advice? I think you're asking the wrong guy to some extent. I have a degree in astrophysics, which is in some ways the exact opposite of life. I certainly wouldn't recommend people go to school to do astrophysics unless they are quite obsessed with it. But this is also similar to a question that was asked in the a much broader sense of the same question that was asked in the if I can find it in the community page. And this question was by Michael Mayhem, which is, what is the meaning of life? And he was answered in the same chat, not incorrectly, with the answer 42. So that exchange reminded me of something that I read recently, which I think is really nice for us to keep in mind when we think about all of this very abstract stuff. So it reminded me of a booklet by the science writer Trevor Quirk called The Thin Air, Metaphor in Science. And Trevor says in this book that, to quote Trevor, that science is not in the business of answers, rather it's in the business of the well-posed question, and quotes Noam Chomsky, who claims that a well-posed question is one that we can imagine a wrong answer to. And Trevor also points out that this is really what Douglas Adams is getting to in Hitchhiker's Guide to the Galaxy. So to remind you non-Hitchhikers nerds out there, in Hitchhiker's Guide, there's a super advanced alien species that builds this most powerful computer in the universe called Deep Thought to answer the question, what is the meaning of life, the universe, and everything? And Deep Thought takes, if I remember, millennia to compute that the answer is 42. The point being that if you don't pose your question well, not only will you not get the right answer, but there may be no clearly wrong answer, which means that even right answers are useless answers, like 42. And asking me any questions about how to live one's life is going to give you a potentially correct but a potentially incoherent answer. That's a long-winded way to get out of answering that question. Okay. I'm just scanning your rapidly appearing questions. Okay, Rana G asks, what do I think of the likelihood of being a Boltzmann brain, and how would I argue against it? Okay, so another one we did an episode on, but a very long time ago. The idea of the Boltzmann brain is the idea that if you imagine that the universe spontaneously appeared due to a random dip in entropy. Okay, I talked about the Big Bang being a moment of very low entropy. If that moment of very low entropy happened just by chance, because entropy always increases by the second law of thermodynamics, but it fluctuates also, and a random dip could lead to a Big Bang, this moment of relative order. And so the Boltzmann brain hypothesis is the hypothesis that it's a thought experiment that says that the chance of getting the sort of dip that would lead to a Big Bang is vastly less likely than the chance of random particles in the void momentarily collecting together into the exact structure of a brain, so that it, for a second before freezing in the void, has exactly your current subjective experience, including your memories of having reached this point in your life, turned on this podcast, and before vanishing out of existence. So in such a universe where you can create big bangs this way, you'll also create vastly more Boltzmann brains that are having your current experience. And so you should then be one of those Boltzmann brains, because there are many more of them, and so just by chance, that's what you'll be. So, I mean, the easy way to argue against it, if you choose to argue against it, the easy way to argue against it is just saying that there's no evidence that the Big Bang is due to a random dip, a random fluctuation in in entropy in an otherwise completely disordered high entropy universe. And there are in fact reasons to not believe that. And so one of the reasons to not believe that the Big Bang just is a coincidental convergence of entropy is that, of all particles to lower the entropy, is that the nature of entropy in the very early universe is the entropy was actually not evenly distributed over all of the manners in which the entropy could be. So, for example, the state of all the particles in the universe was in a state of extreme disorder, in that there was no structure. It was, you could have swapped the places of any two particles in the universe and not change the overall circumstances, okay, which by definition is a high entropy circumstance. The one thing that was in a low entropy state was the gravitational field. And this is a point that Roger Penrose has made, that all of the low entropy in the early universe is bound up into the low entropy of the gravitational field, which you can also translate to being the low entropy of space being very compact, okay? And it wasn't in the particles. So it's a special low entropy state, not a general low entropy state. And I haven't heard a coherent reason why the very early universe was in such a low entropy state, and I don't think too many people are working on it. Of course, Roger Penrose has an idea. I think his conformal cyclic cosmology, in some respects, is a plausible explanation for that. It's a way that these entropy just get to reset every eon. I'm just going to refer to my video on that, then go into it now. But that's a reason to not believe in Boltzmann brains. Another reason to not believe in them is it's not useful to believe in them, that it's an untestable hypothesis, and I think I doubt that Ludwig Boltzmann ever really believed that Boltzmann brains are real. It's a thought experiment to maybe explore some of the absurdities of theory, rather than to make people worry that their brain is going to dissipate into the void in the next second. Okay. So let's go back to a community page question. Okay, so Sylvia Valentine asks, since professors usually focus on a specific area in physics, do I enjoy the opportunity to branch out through this channel? And the answer is enormously. Before I started doing space-time, I was very focused on my subfields in astrophysics, trying to write papers, trying to get the job. And it's a shame that academics don't really get to explore as broadly as they could otherwise, until they get tenure, and in some places not even after they get tenure, by which point they're pretty embedded in their field of study, and it's hard to think outside the box. And so space-time has, in a profound way, helped me stretch beyond my chosen field. You know, I wanted to do astrophysics because I just wanted to be answering interesting and awesome questions about the universe, and exploring the universe in this way. But doing space-time has forced me to become far more interdisciplinary and broad, and I really feel like it's helped me get better at integrating information, and it's even carried across to my research in a lot of ways. You know, maybe this is something I should talk about at some point, but my work now, I think, is broader than it would have been if I hadn't done space-time. And I'm more inclined to bring in novel results from other fields. At the moment, those are in areas of machine learning, you know, which astrophysicists are all over, but I think I've been better than I would have been at, getting into the machine learning papers, looking at what's new, and seeing how things can be brought across. So I think that and that's just the stuff that's obvious in my mind. I think in general, any kind of breadth that you can give yourself makes you a better thinker. Don't dig yourself too deep into your art. Okay. On aliens. Okay, so Blatodophobia asks, when will we discover intelligent life on Earth? Well, this is a contentious topic. So there are some satellite observations that reveal evidence that Earth could indeed support at least primitive life. So there's an excess of ozone and oxygen and methane in the atmosphere, and there's a sort of diminishing green tinge on the surface of some of the planet. And there's some evidence of light sources on the night side of the planet, and they could be some kind of bioluminescence. Now, some fringe theories are saying that this is attributed to cities of some technological civilization, and there are also these erratic radio signals coming from certainly the vicinity of Earth, and they seem to show some correlated patterns, but so far no one has extracted even one bit of significant meaning from any of that. So until we establish some coherent communication with intelligence on Earth, we shouldn't be jumping to conclusions. Rex Lupto asks whether I think that humanity will ever actually reach the stars, or will we keep getting in our own way with drama? So assuming we first evolve intelligent life on Earth, what are the possibilities? This is one that I really prefer not to take a hard position on. So I think if a star-faring future is something that you actually want, I think it's a little dangerous to either be too optimistic or too pessimistic. For pessimistic, it's obvious. If you're too pessimistic, you're just never going to get up and do it. But excessive optimism, I think, has its disadvantages also. Seeing any particular future that you want as inevitable, as predestined for humanity, seeing our future as glorious in any way, I think can make us complacent. And I think it's not guaranteed that humanity won't wipe itself out. It's not guaranteed that humanity has a glorious future, starfaring or otherwise. And I think imagining that it does allows us to ignore very real threats to such futures. And so that's my my word of caution there. I think we have a chance, and I think that fact is incredible, but I don't want to assume that it will be the case. Nerdy asks, how much can I bench? Well, thank you for the question. I bench 1 in my preferred minutes I used to bench 1.5, but then COVID totally killed my routine. Okay, those last couple of questions were from the community tab. Back to scanning your flurry here. Sebastian Pollitt says that their 10-year-old asks whether I prefer Lagrangian, Hamiltonian, or Newtonian mechanics. He uses Lagrangian mostly, but in quantum mechanics uses the Hamiltonian often. So, Sebastian, your 10-year-old prefers Lagrangian mechanics? Wow, a man of exquisite taste after my own heart. Lagrangian mechanics is clearly the superior mechanics. Newtonian mechanics is great if you're like in kindergarten trying to calculate, you know, planetary orbits or something like that. But if you want to do proper quantum field theory, you have to go Lagrangian. Obviously, Hamiltonian mechanics has its place, but it's not manifestly Lorentz invariant. And so if you want to be able to talk about particles moving close to the speed of light, then any self-respecting 10-year-old quantum field theorist needs to go Lagrangian. So thank you for that question. I knew the space-time audience was super intelligent, but I had no idea that their kids were geniuses. Another one on black holes. I always love talking about this aspect of black holes. So Jason Zellman asks, if space and time switch places beneath the event horizon of a black hole and the singularity becomes an inevitable in the future of our theoretical observer who's traveled the barrier, what happens to space in that picture? So to remind everyone, beneath the event horizon, the direction towards the central singularity becomes time-like, which means that your radial coordinate, okay, the inward pointing coordinate after you go below the event horizon, becomes as unavoidable as next Tuesday, as they say. So what happens in that picture to space? Well, the only space dimensions to get flipped in this picture is the radial dimension. So up-down becomes time-like, which means up is in the past, down is in the future, and the other two spatial dimensions stay space-like. So you can still go left and right, just as you could above the event horizon, as long as you're also traveling down. But what happens to time? So time becomes space-like. And what that means is that we can still sense an up-down direction as a spatial dimension. So we still have three spatial dimensions. Time converts into a new spatial dimension, one that takes the place as the old, takes the place of the old radial dimension as an up-down-like dimension to our perception. And it's true that you actually can traverse the time dimension in this picture. Doesn't allow you to time travel with because there's a new time direction which is ultimately going to mess you up. But the old time dimension becomes spatial in the sense that it becomes the new verticality, but it's verticality only in your falling reference frame. So that falling reference frame, is traveling down in what used to be the radial spatial dimension. But in that falling reference frame, you can still imagine a left, right, and an up, down. And time is effectively what you experience as up, down as you're falling. And you can try to travel in that direction, but the only good that does is it changes your position relative to other things that are falling with you. So if something, if an apple's falling into the black hole with you, you can turn on your jets and move up, and it feels like you move up relative to that apple. But in reality, changing your velocity in that dimension either just hastens or slows down your inevitable crushing, your inevitable spaghettification when you reach next Tuesday. or the singularity. Okay, and there is an episode on it, which is how time becomes space inside a black hole. Okay, excuse me for a second. Do some quick ones. Is matter and antimatter annihilation instantaneous, or does the process take more than a Planck unit of time from Wardonis? So the answer is that I think it's sort of not instantaneous, because the particles have to exchange a virtual photon, but that may take less than the Planck unit of time. So it may be effectively instantaneous, but once we're talking about timescales as small as the timescales encapsulated in the exchange of virtual particles of a Feynman diagram, the nature of time doesn't make sense, nor does it travel in only one direction at that level. Federico asks, what is an observer and how can particles, or whatever that quantum stuff is, know when they are observed? I said I was going to answer quick questions, so for that one I'm just going to say, watch our film when we make it, Inventing Reality. What is an observer is a deeply fundamental question. It's the one that kept John Archibald Wheeler thinking and agonizing for his entire life. Radkerson, does a black hole spaghettify even the smallest subatomic particles? So now we're now again into the quantum nature of the substrates of the universe of are the smaller subatomic particles really point-like, or do they have an extent? So I think to answer these questions, you need to go to things like string theory, where you would need to ask, is the singularity of a black hole smaller than a subatomic particle? And I think the answer is basically no. I think maybe there are tidal forces. There can be tidal forces on the subatomic particle, but the nature of a singularity, well, I think it's sort of yes and sort of no. I think the nature of the singularity in the black hole is probably, in whatever our theory of everything or quantum gravity turns out to be, it probably will have some extent, and the size of that extent will depend on the theory, but it'll certainly scramble subatomic particles in some respect. Okay, so I'm going to answer a question now that was in the community tab, which is it's one that I wouldn't jump into normally, except that it seemed quite popular. And this is by Caitlin L. What is my preferred answer to paraphrase, to the determinism versus free will question? And Caitlin notes that I previously kept my own preference out of the matter, although I've hinted that I favor free will. So firstly, I think the first part of the answer to this question comes from Douglas Adams and Noam Chomsky, which is that for a question to be scientifically meaningful, it needs to be properly formulated. And I think the question, do we have free will, or is free will an illusion, is a horrifically loosely and badly formulated question, and it doesn't in itself have a real answer. And so I think anyone who thinks that the answer is obvious in the context of determinism is may themselves be a good scientist, but they're doing bad science in the notion that they can give a scientific answer without formulating that question properly. And the formulation of that question requires much more careful definition of the terms involved. So that said, let me give my hot take. So the question implies that we have to either choose determinism or choose free will. And my position is that it's not just a badly formulated question, this is a false dichotomy. So the concept of free will, in my thinking, is perfectly meaningful, even in a deterministic universe. And Sam Harper pointed out in that same community tab question that the position where free will is compatible with a deterministic universe or a mechanistic or even a random universe is called compatibilism. Sorry, my mouth doesn't work. And Sam also points out that physicists don't seem to consider compatibilism or reject it out of hand, but it's nonetheless the dominant view among philosophers. Now, it is a dominant view among philosophers. I'm not sure if it is the dominant view, but you might know better than I do. And so I feel that I mean, physicists know the word compatibilism, but I think they misunderstand the notion. And I think part of the reason is that philosophers don't present this position in a language that physicists understand. So let me very briefly lay out a framework that might be more compatible with physicists. And I'm going to keep it brief because I have another shout out for you, which is that, so there's an excellent podcaster, YouTuber, Kurt J. Mungle, who has this podcast, Theories of Everything. And you can look at his YouTube channel, and he's interviewed some really incredible thinkers there. And also me. We had a long conversation last week, and I think that this will be posted later on this week. For some reason, this particular question about free will came up, and he goaded me into giving my hot take. And so I'm no longer able to even pretend that I don't have a position. So I'm going to give you a super brief overview, but I encourage you to go to Kurt J. Mungle's Theories of Everything when this goes live. It's not live yet, but the upshot is that let me lay it out a little bit. So the act of choice, okay, the act of freely willing something, is a phenomenon within a particular dynamical framework, okay? And it's a phenomenon that's in the dynamical framework of the mind. We can think of the mind as a causally closed system. So it's a dynamics of thoughts. Thoughts lead to thoughts, lead to thoughts. And in some respect, it has its own mechanics. Now, within that system, there are things that cause other things. Okay, so you can define a causal potency between the elements within the system of your mind. Okay, and the same is true of many other types of systems that are thought of as emergent. Okay, so for example, you can change an ecosystem by introducing an animal that has some causal influence on the ecosystem. The Fed can change the interest rate, which has a causal influence on the economy, but I think it's silly to say that an element within a causal system, within some dynamical system, doesn't have a causal power within that system just because the system is in some way emergent from some more fundamental substrate. Again, I think saying that free will is an illusion, or that one doesn't have free will because of the substrate, is a fallacious misunderstanding or mixing up of the definition of the idea of cause. Okay, so within a dynamical system, emergent or not, and you could argue that there are no dynamical systems that aren't in some sense emergent. That's another topic. But so there are these two types of causal power. There's a type of causal power in how, for example, Neurons are made up of molecules, which are made up of atoms, which are made up of quantum fields. Okay, so in a sense, the smaller things cause the bigger things. And that's also true of dynamical systems that aren't simple hierarchies of scale. Okay, you could argue that money and transactions generate economies or have some causal effect on the events within economies. But saying that thoughts are caused by neurons or are caused by the electrons in the action potentials or are caused by the fundamental strings that make up the electron, saying that these things are have a causal power over thoughts is the same as saying that money causes economies or that animals cause ecosystems. So you see that there are two ways to think about cause. One is a cause within a dynamical system, and only elements within that dynamical system cause other elements within that dynamical system. And there's the type of cause where one level of, say, either a scale or a complexity hierarchy causes a higher level, an emergent level. And that's a generative cause. The substrate generates the new system, but doesn't. And you could say that it could cause the components of the system, but it doesn't cause the dynamics of the system. The dynamics have a kind of a closed causal network. They cause themselves. Okay, so the causal power within an emergent system sort of lives within a system and entities that are defined within the dynamics of that system. So our choices have causal power within the dynamical system that we call the mind. So do you have a choice in anything that you do? So I think framing the question, do you have a choice, sort of externalizes the notion of you from the system in which that choice is a dynamical element. So that's in a way as meaningless or as fallacious as saying that there's a needle that plays the mind in a block universe, or even that our minds contain some, homunculus that watches the output of our brains like a movie. You are the dynamical system of your mind. So with respect to the you in that definition, your choices are very real. They are the most real things because they're part of the dynamical system that you are. And they're not even caused by your neurons in the sense that your mental dynamics are, another rabbit hole is dualities, but your mental dynamics are in a sense dual to your neural dynamics. It's another way to frame the evolution of that system. But the causation, for any reasonable definition of causation, lives within the dynamics, or at the very least can be thought of as going in both directions. And one last point on this topic is that, let me say why I don't buy the idea that none of this matters, because we live in a mechanistic universe and that everything's either predetermined or random. So I would say to that, if you don't have free will, because there is some observer that you could imagine who could, by knowing the exact state of all the quantum fields in your brain, predict your next action and be 100% correct about that prediction, then I would say to you, what observer? And can that observer really exist? And the answer is essentially no. In a system as complex as the brain, it essentially requires Laplace's demon to perfectly predict your behavior. It is a highly chaotic system. You essentially have to know the exact quantum state of every particle in a brain to perfectly predict the outcome, sometime in the future. And so there isn't an in-principle observer who could do it. An in-principle observer is an observer that could exist in principle, far future technology or whatever. There are only fictional observers who could do it. And so if you're going to rule out free will because a fictional observer that you could imagine could predict your behavior, then you need to rule out everything that every fictional observer that you can imagine is able to negate. As I said, that was going to be a brief replay of my thoughts on the matter. Go and watch Kurt's podcast in general because it's awesome, but watch my version of it. This is also something that surely we will talk about in Inventing Reality. So guys, we are now an hour and we've gone pretty deep, I think. However, if you still have some appetite for asking Matt anything, tomorrow I'm doing an AMA on Reddit, okay, on Ask Science. The thread will go live in the morning, relatively early, and it would be amazing for as many of you as feels like it to go in and ask questions, because I swear you're going to have the best questions, and those are ones that I would love to answer there on Reddit. I'll start answering, around noon or something like that, and let's try to hit the front page. That would be fantastic if we can do it. We did it last time, but that was years ago. And if I didn't get to your question, and there'll be unfortunately many of you, then I'm going to actually be able to answer a lot more tomorrow, I think. So let's see if we can. All right, everyone. This has been really fun. Hopefully it'll be less than a year before our next State of Spacetime. I wish you all a wonderful holiday season, whatever you're doing. And yeah, I'm excited to make another year of Spacetime with you all. Well, I'll see you on our next episode of, I can never think of the witty ones when I come to it, so Spacetime.